So welcome to what is, I think, the 5th video in the motion topic. This video is slightly longer than the others. The first half of the video is essentially the theory, and the second half of the video is a worked tutorial solution. So in this video, I wanted to clearly state the problem-solving methodology that I use and how I apply it to motion questions, and then give the example of a two-dimensional case. The reason is that I think the problem-solving methodology is a fundamental tool, not just for scientists and engineers, but also just in life in general. And it's something that's very often implied through the way we solve the problems, but it's not explicitly stated. And I think that explicitly learning the methodology, or explicitly teaching the methodology, is one of the more important things that we can teach the students, and it's definitely something that I wish I had been taught. So if we start with one-dimensional motion and we translate it into a problem statement, so into a semi-mathematical statement, I would say that the motion is a linear combination of vector algebra and the equations of motion, and likewise in 2 dimensions. And in 1 dimension, we know all these things, that's no problem, so there's no surprises for us. In 2 dimensions, vector algebra in 2 dimensions means we need to know vector addition and subtraction, which means we need to know how to work with vector components, which we can do. And the only thing we don't explicitly know as yet is the 2-dimensional equations of motion, which means essentially we resolve our 1-dimensional equation into 2D vector components. So if we look at our 1-dimensional equations, the 5 of them, to resolve it or to use them in a 2-dimensional case, we just need our horizontal and vertical components. And so we just do that for each of our equations, and then the right hand side of the slide gives us our 2-dimensional equations of motion. So since we now know essentially everything we need to know to solve motion problems, really the only thing that they can do to us is to confuse the question with the way that it's phrased. And indeed, most of the mistakes I come across either because the student has mistranslated the problem statement and found the wrong quantity, or because they've got themselves mixed up or lost solving the equations partway through the problem. And as a high school student, I did both quite thoroughly. So there are 2 things I do to make sure I don't end up confused. So the first thing I did was I had my general method that I followed, a standard method. And for me that was really useful because in an exam, if I was stressed or if the question was phrased and twisted in a strange way, I at least had this concrete method that I could follow to solve part of the problem, if not all of it. And the second thing, and the hardest one for me, was to keep it neat. So to keep my page neat, which in my case required an awful lot of practice. So this is the general problem-solving methodology that I use. It obviously doesn't need to be followed as formally as I will present it, but I think at least it's a good place to start. So step 1, and you will hear me say this 1,000 times, is to translate the problem. So what I mean by that is, first of all, find out what it is we need, so what the problem is asking us to find, and translate that into a mathematical statement. And second, to find out what it is that we have, so what information the problem has given us, and that includes doing things like drawing a diagram, and in that case including your coordinate system that you use. So for example, if you choose that north is in the positive y-axis, then include that in the diagram, and to write out the variables that you have. And at this point, this is when I translate those variables into SI units, again, because that was a mistake that I used to commonly make. The second thing to do, once we have the information, is to find the tools that we need to use. So in the case of motion, that means that given the information we have in number 1, so what it is that we want and what we've got, which equations of motion would be most useful for us. The third part then, and this is obviously my downfall, is to organise it all. And by that what I mean is to work out your precise method that you will use to solve the problem. So which equations you'll solve and what they'll give you, and in which order you need to do it. And once you have all those things, then you can finish it all up and check it. So that means you finally solve your equations, you check that you've answered the question. Again, this was one of my downfalls, And then if you haven't quite finished answering the question, repeat the process. So on the next slide, I'll work through a two-dimensional example using this method. If we're given a two-dimensional acceleration and the initial velocity of the leaf. So the first thing we do is you find what is it that we want. So what's the question asking us to find? And it's asking us to find the final velocity of the leaf when the displacement of the leaf equals 12 meters in the x direction. So when Sx equals 12. And it's asking us to find it in the magnitude and direction format. What we've got, so because this is a two-dimensional motion question, I set this part out as follows. So I split it into the horizontal and vertical components, and under each part I write down each of the variables that I could possibly have, and I always put t in the middle because the same t applies to both horizontal and vertical. And then I fill in the values that we get from the question. I do generally put a box around it when I'm writing it on paper so that I can separate it from the rest of my reasonably messy working out. So now we know what we want and what we have. We can look at what equations we need. So first of all, we're asked to find the magnitude and direction of the velocity. So we need equations for that, and those we know. We know that it's a two-dimensional velocity, so it will have an x and y component, and we know that from those x and y components we can calculate the magnitude and the direction. I haven't specified which formula I will use to calculate the direction in terms of theta. I'll choose that later once I have all the other information. The second thing we need then, or in order to solve this, we need to know our x and y final velocity components. And to do that, we need to use our equations of motion. So again, because it's two-dimensional, I split these equations into the horizontal and vertical components. And I look at what I have. So in the horizontal direction, I've been given my initial velocity, the acceleration, and the final displacement. And I want to find the final velocity. So I will use this equation because it allows me to calculate the final velocity directly. In the vertical direction, I can see I've got less variables, so I've only got two variables. I've got my initial velocity and my acceleration. I want my final velocity, so the equation that I think is most likely to be helpful is this one. But in order to find the final velocity using that equation, I still need to find t. So to find t, I can choose any of my other equations of motion. In this case, I'm choosing this one because I have all the variables I need. So now I have my tools. The next step is to find the method that I will use, so explicit method that I will use. So first up, I'm going to solve my equation 1 for my final velocity in the x direction, the x component. Then I will solve equation 3 for t and use that t to find the y component of my final velocity. And once I have those two things, I'll use them to find what the question has asked me for, which is the magnitude and direction of the final velocity. So now I've set up my method, I can solve. So step 1 is to solve my equation for Vx, which I can do directly. And once I have my value for Vx, I put that into my variable box. Step 2 was to solve equation 3 for t. The equation that I've chosen requires that I use the quadratic formula. And I find t is 1.5 seconds, and again I put that straight back up into my variable box. And then the final step with these equations was to solve for Vy. So now I have all the information I need, and I can find my Vy. And again, I pop it up in my variable box. So now is a good time. Now I've done a lot of equation solving. Now is a good time for me to check where I'm at. So I have done steps 1, 2, and 3. And all that's left for me to do now is to actually answer the question. So I will draw my diagram to find my final velocity. I have my Vx and my Vy. I know this is what my final velocity looks like from a two-dimensional vector addition, and this is the direction that I'm looking for. And then using my standard equations, I can solve for the magnitude of my velocity and my direction. And the very final step is to actually answer the question with my problem statement, giving the magnitude, the units, and the direction. So on the following page, or on this page, I've given you 2 one-dimensional examples, questions to solve, and the answers and the worked solutions using the methodology described in this video are given just in the next video down the page. Enjoy.